Through the problem introduced here, we are thinking about how to deal with variable linear coefficient of thermal expansion. In the previous problems, the linear coefficient of thermal expansion is assumed to be constant. We have solved problems assuming that the linear coefficient of thermal expansion does not vary at any temperatures. In reality, however, the linear coefficient of thermal expansion varies being influenced by temperature. For example, the coefficients around 0 degree and those around 100 degree is different. This is the general behavior of an object. Sometimes, the linear coefficient of thermal expansion is approximated as a function of temperature. Suppose the value of linear coefficient of thermal expansion is constant. The related calculations are very simple. In this problem, the linear coefficient of thermal expansion is given as a linear function of an absolute temperature T. We then find the thermal strain that is generated when the temperature of this object is increased from 293 Kelvin to 353 Kelvin. So far, the problems can be solved by considering only the amount of temperature change. In this problem, however, the linear coefficient of thermal expansion, which is given by the following function, varies depending on the temperature. In this case, we cannot calculate directly by using delta T as in the problems before. So, we are solving the problem in the following procedure. The function of linear coefficient of thermal expansion, alpha T, should be multiplied by a small fraction of temperature. Then, we get a small fraction of thermal strain. Here, we notice that the linear coefficients of thermal expansion multiplied by a small fraction of temperature is a small fraction of thermal strain. So, we are going to take the sum from 293 Kelvin to 353 Kelvin. As the result of the sum, we get the total thermal strain. This is almost the solution to this problem, but you should perform the integration by yourself and confirm that the thermal strain is 596 micrometer as the strain. Anyway, we noted that when the linear coefficient of thermal expansion is temperature dependent, you must perform integration. The thermal strain can be calculated as the product of linear coefficients of thermal expansion and delta T only when the linear coefficient of thermal expansion is independent of temperature.